Hello grade 11s, welcome back to another lesson. We are continuing with our Euclidean Geometry series. As you can see with the heading there, today we are going to go through a couple of examples. Just a recap in terms of what we've covered before. If you are joining for the first time, lesson 1 we discussed we did a revision of grade 10 theorems, and we introduced we did a basic introduction of grade 11 theorems. And then lesson number 2 we went through what we called examinable proofs by doing first principle there. Also very important lesson that you need to catch up on. And previously on lesson number 3 we were exploring theorems. So as we know, we've got about 10 or so theorems. These theorems are divided or are categorized into 3 sections. We've got one section where theorems fall under centers of a circle, which is what we're going to discuss in this lesson, but we'll be doing a couple of examples. And then category number 2 or section number 2 is theorems that falls under cyclic quadrilateral, which is what we're going to cover in the next lesson. We'll do the examples there, couple of problems. And then category number 3 or section 3 is theorems that falls under tangent, which is a lesson that we're gonna do later on. So we are starting to get into, so I would say so far we've covered most of the theory. We'll also touch a bit of theory in this one, but we are starting to get to the real core of Euclidean geometry, which is solving problems, okay? And which is what mathematics is all about, solving problems. Okay, so without wasting time, grade 11s, and let's get going. Okay, so I've made some notes here in terms of a couple of tips or steps that you need to follow before attempting to solve these problems. The first one here, I've got 5 bullets here. The first one, it says, when you get a problem and you solve a geometric problem, you need to mark off all radii and consequently all base angles of an isosceles triangles. Okay, so this is only for this section of theorems that falls under center of a circle. Okay, number 2, it says, if given that a chord is bisected, mark off the 90-degree angle formed by the perpendicular line from the center of the circle. Very, very important. For all diameters, mark off angles subtended at the circumference equal to 90 degrees. Okay. Check each angle at the center, mark it as 2x, and mark off the angle at the circumference as x. I'm sure you know what theorem is this one. Angle at center is the angle at the circumference. And then lastly, mark the 90-degree angle formed between radius and tangent if you are given a tangent. Okay, so this one mainly we'll look at it when we look at the category of tangents. But I just want you to pause for a second, make notes of these tips or bullets, and then you'll see how I apply them when solving problems. Okay, so let's jump over to examples. Okay, so that is our example number 1. It says, and very important, that's much better. It says O is the center. Okay, very important. So that's something that we need to start by marking on our diagram. So it says O is the center. This big one there. Okay, it's the center, O there. AB is equal to 8 centimeter. So from A to B there is 8 centimeter. And I want you to follow the steps that I'm following, that I'm doing here. Okay, it says AB is equal to 8 centimeters. So I'm going to read the whole introduction there, or description or statement. It says AB is equal to 8 centimeter. OF is equal to 3 centimeter. OE is equal to 4 centimeter. AF is equal to FB. And CD is perpendicular to OE. Calculate the length of chord CD. Okay, that is me reading the statement first. Okay, now I'm going to read it again and make sure that whatever that is being said here, just to confirm if it's also shown in the diagram below. Okay, so you say O is the center, so there was no O, but I know that this is O, which is center. AB is equal to 8 centimeter. The moment they tell me that, let me get the color. A to B, it's 8 centimeter, and I can see that I've got two lines there that shows that these lines are equal. Then I know that here is going to be 4 and here is going to be 4. That is common sense. No need to panic about this, okay? And I know that this diagram, it involves a theorem number 1 that says a line drawn from the center of the circle perpendicular to the chord bisect the chord, okay, which is what is happening from here up until there. Okay, then it's telling me that OF is equal to 3 centimeters. So I will check what is O, what is F. Okay, now I seems to be having a problem. Where is F? But this guides me to say where is F. So it says AF is equal to FB. So my F must be here. Okay, so O to F is what? It's 3 centimeters. I'll put my 3 there. And then OE, where is E now? I've got another problem. So it looks like E will be here. How do I know that E is there? Because it's telling me there that CD is perpendicular to OE. So CD is perpendicular to OE. So my E can only be here. I don't know why E and F were not shown in the diagram. Maybe it's a typing error or what, but it's very important to link the statement with the diagram. Okay, OE. So this is 90 degrees. It's telling me that OE is equal to 4. Very important. And it says calculate the chord CD. So I must calculate CD. So for me to get CD, there's a couple of things that I need to do first. So this is where I'm going to start. I'm going to start by saying, okay, Mr. Examiner, this is how I go about my calculations. Okay, I'm going to say, and very important about Euclidean geometry, statement, reason, statement, reason. If you put a reason or a statement without the reason, you're not gonna get the marks. Okay, so where did we start? We start by saying AF is equals to B, which is equals to 4. How do we know this? It was given. It was given. It was shown that these lines are equal. So it means if that is 8, then therefore these lines can only be 4 units. 4, 4. Okay. And then OE is equals to 3. It's also given. There's not much that I can do. Then I'm going to say in triangle OAF. Okay, I'm working in triangle OAF. I'm going to say, as you can see, it's a right angle triangle here. It has to be a right angle triangle because of the theorem 1, which is a line drawn from the center perpendicular to the chord. Okay, so I've got the right angle triangle, so I'm looking for this radius. Okay, so we know that radius is equals to, which in this case is equals to OA, is equals to the square root of, we are in grade 11 and I believe that we know how to solve and how to apply theorem of Pythagoras. So we're gonna have 3 squared plus 4 squared, but I need to put reason in there. I need to say theorem of Pythagoras. I need to tell the examiner that this is a theorem of Pythagoras. Then this is going to be what is 3 squared is 9 plus 16, the square root, which is the square root of 25, which is equals to plus or minus 5. But because radius is always positive and we're dealing with length, OA can only be positive. So it's going to be positive 5. So I know that I've got 5 there. So this is a radius, okay? And if you recall on the tips that I showed on one of the slides, it says you need to mark off all the radiuses. So I'm going to say, I know that I've got radiuses here. So this is a radius. It's 5. So it's from the center to the circumference. This is also a radius, is from center to the circumference. So if this is 5 and this is, if this is a radius and this is a radius, it means if this is 5, this is also 5. Okay. Now, if this is 5 and this is 4, and here we've got 5, 4, and the other side is 3, it means this side must also be 3. And if O to E is perpendicular to C and D, it means this side is equal to this side. And if this side is 3, and then it means this side is 3. And if this is 3 and this is 3, it means CD is equal to 6 units. Very, very important. Here is all about building blocks. Where do you start? How do you go about it? How do you link the statement to what is being shown in the diagram? Like I said, here we are doing examples. I don't want to dwell too much into how to write your reasoning, how to write your statements. We will do that when we solve riders. Here I just want to show you how to solve these problems. Hence you can see here, I'm just writing all over the place. The most important thing for you is for you to see the steps that I'm taking to get to the answer. And that concludes this example 1. We will now jump over to example number 2. Okay, example 2 goes as follows. I'm going to start by reading the statement. So this statement, I call it the love letter. So read the love letter first. And why is it important to read the love letter? It's important to read the love letter because what is given here as a statement, sometimes it's not shown in the diagram. Okay, so I'm going to read this first. Just read to understand what is there, then I will come back and I will link what is on this love letter to what is there on the diagram. So it says AB is a chord of a circle with center O and is 24 centimeter long. Okay, C is the midpoint of AB. C is perpendicular to AB and it cuts the circle at E. Calculate the value of X if CE is equal to 8 centimeter. Okay, so I read the love letter first just to get an understanding of what I'm dealing with. Now I'm going to go and highlight all the important points there. AB is a chord, so AB is a chord I can see of a circle with center O. So the moment they're telling me about a chord and they're telling me about the center, what do I know? Line drawn from the center of the circle perpendicular to the chord bisects the chord, or the perpendicular bisector of the chord passes through the center of the circle. That's theorem number 1 and it's converse. So I know I'm dealing around those type of theorems. Again, going back to my tips, or the tips that I showed you there, it says once you've got center and you've got radii, mark off those radii. So I'm going to mark the 3 radii, and then I can just put a note there that OB is equals to OA is equals to OE. So I'll just put a note there that these are my radii. So I'm not sure if I'm going to. So solving these geometric riders or problems, it's like building a house. When you want to build a house, you need to buy material. You need to buy sand, you need to buy bricks, you need to buy cement. So this is me buying all the material that I'm going to need to build the house. But in this case, to solve this problem. Okay, O is the sand is center O and is 24 centimeter long. So because I know I'm dealing with perpendicular bisector of the chord, I know that this line is equal to this line, and you will see here I'm using 2 lines here because I've already marked this as my radii, so I can't put one line there. So that's why I'm showing that this one is AC is the same as CB, but it's not the same as all the other radii that are there. So AC is going to be 12. How do I know that it's 12? Because I've been told that AB is 24, so 12 plus 12 is 24. How do I know that these lines are equal? Because you've got the line which is the radius that is coming from the center of the circle, passes through the chord, and it bisects, it cuts the chord in half. Very, very, very logical. Very, very important. You must flow when you're solving these problems. Okay, C is the midpoint of AB, and C is perpendicular to AB and cuts the circle at E. That is what we know. And you will see here, ladies and gentlemen, I'm not worried about, writing the steps, giving statement reason, giving statement and reason. Here I'm just showing you how to attempt these problems, how to link what is on the love letter, the statement, to what is on the diagram. You will see on the next coming videos or lessons when we start solving geometric riders, when we are attempting questions from previous exam papers. That's when now I'll show you how to answer like you are writing an examination, how you need to impress the mark. Okay, we'll get there. Now I've marked all of this and I need to determine the value of x, and I'm being told that CE is equal to 8 centimeters. So I'm just going to put it there so that you can see nicely. Now if you look at this triangle here, I've got a nice triangle there. I've got O, I've got C, I've got B. So I don't know what this length is. This is what I'm looking for. I know that here I've got 12 and I've got C, X there, sorry. And from here I can see that I'm dealing with an RHS, right hypotenuse triangle, because this is a 90 degree. So once I'm dealing with this, I know that I must use Pythagoras theorem. Every time when you see a right angle triangle, every time you see theorem 1, line drawn from the center of the second perpendicular to the chord, just know that you are going to apply theorem of Pythagoras somewhere. And theorem of Pythagoras is what we've covered in the previous grade. So it doesn't mean that we are done with it, we are no longer going to use it. No, we are going to continue using it. Hence, on my lesson number 1 of this series, of this geometry series, I mentioned and I emphasized the importance of revising earlier grades work. So it means work that is covered in grade 10, grade 9, and as far as grade 8. Okay, so I've got the right angle triangle, so I'm looking for OB. So I know my OB squared is equals to OC squared plus CB squared. So and I need to put a reason there. Theorem of Pythagoras. No reason, no answer. No mark. So statement, reason, very important, which is what is key when it comes to Euclidean geometry. So I'm going to substitute there. So my OC is x, so I've got x squared plus 12 squared. I'm going to simplify this. I'm going to have x squared plus 144. I don't know why. I must not have this because I already have a square root there. So OB is equals to x squared plus 144. But OB is equals to what? OB is equals to so OB is equals to what? Is equals to OA, which is equals to OE. These are what we call radii. Therefore, OB is equals to OB is equals to OE. And what is OE? OE is equals to OC. OB is equals to OE. Okay. OB is equals to OE. It's coming from there, radii. But what is OE? OE is O to C, E to E, C, E. Therefore, I can substitute. Where I see OB, I'm going to substitute X, or OC is X, CE, it's 8 units. I'm going to scroll down. So it means where I see OB, I can substitute X plus 8. So I will come back here. I will come from here. So I will come here and I say OB is equals to square root of x squared plus 144. What is OB? Where I see OB, I can substitute x plus 8. So this is x plus 8. The square root of x squared plus 144. From here, algebra. You can't run away from algebra. Okay? So now I want to get rid of the square root. So we need to solve for x. I'm going to put a square there. What you do on the left, you also do on the right. So from here, I'm going to have x squared plus 16x plus 64 is equals to x squared plus 144. This is not an algebra lesson, this is a geometry lesson. So I believe you know how to do this. I'm not going to waste time and show you the steps that I did to foil this. You should be confident enough to solve this. No, yeah, sorry about that. Had some load shedding there. Anyway, let's continue. We blame everything on ESCOM. Everything that goes wrong, blame it on ESCOM. So, like I said, this is a Euclidean geometry lesson, so I'm not gonna dwell too much in terms of what or how I got there. Okay, so I can cancel the like terms because they are there. Then I put all the variables on one side, so I'm gonna have 16x is equals to 144 minus 64. I'm gonna get 80. Therefore, x is equals to 80 divided by 16. It's 5. So it means 5x is equals to 5 units. But wait, is it units or is it centimeters? Oh, so it's centimeters because we were given there that it's centimeters. So if they don't specify what is there, you write units. But if they give you meters, you write meters. If they give you centimeters, you write centimeters. Now my eraser doesn't want to work. So it's 5 centimeters. And that concludes this problem. Very, very interesting question, very important question. You will most likely, 95% of the time, be asked a question like this in an examination. So you need to know your basics. Now let's recap what we did, or what we've learned from here is that you need to mark off your radii. Your radii are very important because they help you to link what is given and what is not given. Also, we applied your theorem number 1, line drawn from the center of the circle perpendicular to the chord. And we've also learned that if you've got a right angle triangle, you will most likely use your Pythagoras theorem. And you use your Pythagoras theorem, you link your radiuses, you check what is given, you check what you need to determine, what you need to solve, you link the two, and then the rest is history. Algebra, algebra, algebra. You can't, how do I put this? The mere fact that we are dealing with Euclidean geometry doesn't mean that you can apply your algebra. That's why algebra, in most cases, in most of the books, it's your chapter number 1, because you need it as a basics to apply it in other chapters, in functions, in financial maths, in calculus. When you get to grade 12 next year, you do calculus, you're going to need algebra. So you can't miss that. So that concludes this example, grade 11s. We will jump over to example number 3. Okay, grade 11s, let's look at example 3. And as mentioned, we're gonna start by reading the first, or we're gonna start by reading firstly the love letter, your problem statement, and then we will link that to what is there on the diagram and see what is required of us. Okay, so it says O is the center of a circle ABC, right? AC is produced to D, so that CD is equals to CB. Prove that O1, so this must be here, it must be O1, prove that O1 is if D is equals to 32 degrees. I love this type of questions where they ask you to prove and they give you the answer. So like they are telling you what the answer is when I just need to work around getting that answer. So before you even leave the examination room, if you get that O1 is 128 and you've shown all the steps and you've given the reasons, you've already know that you got this answer, this question right or wrong. That's what I love about proving this type of questions, or this type of questions where you need to prove. Okay, so let's read the love letter again. So this is our love letter problem statement. It says O is the center. So what do we know when we've got a center? We know we've got radii. So this radii is the same as that, but already the BC is shown with a line there. and see this one as a line. So I can't put a line here. I must put two lines so that I show that these lines all together, they are not equal to each other. Okay, so we've got radii OA and we've got radii OB, they are equal. Okay, that's fine. Anything else about O? So nothing more. And I think I see some kind of an arc there. I see an arc that subtends an angle. I see an arc BA which subtends an angle O1 at the center. And again, the same arc subtends an angle C1, which is half the angle of O1. Okay, we'll get to that. So there's a possibility of an angle at center is twice the angle at the circumference theorem here. Actually, it's there. You can see it. If you tilt your head, you'll see that we've got something like this. Okay, so that should be in your mind. AC is produced, so nothing much about produced. So the only thing that you need to keep in mind about produced is straight angles. So you just need to straight line angles. So every time you see this, just know straight line angles. So angles on a straight line, they add up to 180 degrees. That's pretty much about it. So that CD is equal to CB. So they've already shown us with a line there, these lines are equal. So what happens when lines are equal? So when this is equals to that, we've got what we call an isosceles triangle. Isosceles triangle. What do you know about an isosceles triangle? Base angles of an isosceles triangle are equal. So it means this angle is equal to that angle. Okay? Very, very, very important. This is how you flow with answering this problem. That's why I love Euclidean geometry so much, because it's a building block. It's like you're moving from one stage to another. No, from one grade to another. Grade 4, grade 5, grade 6, grade 7, grade 8, grade 9. That's how you need to flow. Okay? Okay, they're telling me that this is 32. So this is where I start. Remember I told you that I'm not going to write a lot of things. I'm just going to show you how to get to the answer. So we need to determine O1. So we need to get the value of OY. But we are told that D is equal to 32. So I'm going to put 32 there. So 32. And I've already mentioned that D is equal to B2. So this is 32. Why are they equal? Because these are base angles of an isosceles triangle. BC is equal to CD. How do we know that they're equal? Because they are given to us. Given. Alright. So if this is 32 and this is 32, what is C2? C2 is going to be 180 degrees minus 2 times 32. Why? Because angles of a triangle, some angles of a triangle add up to 180 degrees. Okay, so this is going to be 116. So I'm going to put 116 there. So we've got all these angles here. What do we know about produced angles on a straight line? So if this C2 is 116, it means this angle must be what? 64. How do I get 64? 180 degrees minus 116. I'm going to get 64, which is C1. Remember I said here, I'm not really interested about writing here. What I'm interested on is filling up this diagram. So fill up the diagram. Fill up the dome. Fill up Orlando Stadium. Fill up this. So as we are filling up the diagram, okay, maybe that's the hashtag that we need to put in place here. Fill up the diagram. Now, if that is 64, and what do we see? We see that we've got what we call angle at center is twice the angle at the circumference. How do I say that? Only my two eyes. Now it looks like my pen doesn't want to write. So I'm going to highlight that so that you can see. So you can see this. Man, doesn't look like a highlighter is the best. It's the best that I can do here. Let's look at this. So this arc, and this is how you subtend an angle there. Okay, the same arc subtends an angle there. What do we know about this? Angle at center is twice the angle at the circumference. So if this is 64, it means this is twice 64. So it means this is 64 times 2. What is 64 times 2? 4 times 2 is 128. And we have proven what was being asked there. So, grade 11s, this is very important, and I don't know how to emphasize this. Before attempting to solve those difficult geometric riders, attempt the small ones. Learn how to build up from what is given. Learn how to link what is on the love letter, what is on the problem statement with what is there on the diagram. Again, you cannot solve these problems if you don't know your theorems. So that's why I took time. I went through the introduction, I went through examinable proofs, I went through exploring these theorems so that I make it easy for you to understand these things, to flow like the way I was flowing. Hence, it's easy for me to get these answers. But what is very key is to be able to link what is on the problem statement with the diagram. And the reason they tell you that O is the center, that is an answer. So that information is going to help you to answer a problem. The reason they tell you that AC is produced, that statement is going to help you. The reason they tell you that CD is equals to CB, that information is very important, it's going to help you. So everything that they say on the problem statement, on your love letter, one way or the other, you need to apply it. I hope for the third time, since this is example number 3, that when it comes to centers, angles or theorems that falls under centers of a circle, you are now starting to get to the habit of applying the theorems. Theorem number 1, line drawn from the center of the circle perpendicular to the chord bisects the chord. The perpendicular bisector of the chord passes through the center of the circle. Angle at center is twice the angle at the circumference. Those are the key things that you need to know. Having said all that, grade 11s, until we meet again, have yourself a wonderful